All right, video going over, let's see, enthalpy, entropy, and Gibbs free energy. Look at that. Three things that are basically, in chemistry at the very least, like the major things we talk about in thermodynamics. At least, again, like it could get way worse, but for like an introduction to chemistry, a high school chemistry, right? These are the three main ideas that if you understand these, you have a pretty good idea of the thermodynamics as a beginner, right? And then it can get more complicated. There's more things you could talk about. There's certainly more complexity you could add to it. If you take physical chemistry, all right, take a class called thermodynamics in college, right? It can certainly get a lot more challenging. But this is a good backbone to build on, right? This is a good foundation. That's true. That works. So why complain, right? Or rather, why make it worse than it has to be for right now, right? So anyway, we have three ideas. Okay, we have, let me change the size of the marker, I guess, right? There we go. That's probably good. Right, we have enthalpy, enthalpy, we have entropy, and then we have the last one, kind of a mouthful, the Gibbs free energy. Okay, these three major concepts. Okay, enthalpy, to make it simple, is essentially heat or energy that is either released when a substance is made or needed to be put into it in order to make something. AKA, this is basically like any substance you think in chemistry. If I were to make it, the enthalpy of formation, as the name suggests, is how much enthalpy is needed to make it. And enthalpy is a fancy word for heat. Okay, technically it's heat at constant pressure. Okay, we're also ignoring what's called work. Work would be like if you had an expanding balloon. The balloon is pushing on the air. The balloon is doing work on the air. It's causing expansion. That takes energy. Okay, just like if you push something up a hill, that's work, right? So too does expansion of something, or on the flip side, contraction of something, right? But again, that's kind of above the scope of this class, okay? So enthalpy is just heat. And you can think of this as in an exothermic reaction. If the enthalpy change of a reaction is negative, the implication is there's extra energy that is leaving. Okay, negative, think of it as exiting. Negative is get me out of here. Energy leaves, it's exothermic. In a reaction where the enthalpy change is positive, right, it implies there's more energy going into the reaction than out. That would be an endothermic. Energy is entering the reaction. Okay, you need energy to go in for it to happen. Whereas exothermic, you can think of it as energy is in surplus, extra energy that can leave. Okay, so that's enthalpy. This comes from the bond energies, all right, which is a little bit easier to think about with bond energy because for a bond to be made, right, let me grab one of my little modeling kits here, right? For a bond to be made, okay, it always releases energy. When two things come together, it releases energy. So if I had, for example, this chlorine and this carbon, okay, if I want to break this bond, it takes energy. Like I have to put energy in to break it, okay? The flip side is when they come back together, it releases energy, okay? Energy cannot be created or destroyed. And energy is what's called a state, well, at least in this context, it's a state function, which means the energy going in, out, whether I do this 5 times and then I do something else to it and do something else to it, blah, 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 the amount of energy to do this step is always the same, okay? State functions are a little more complicated, but just to make it simple, the energy to make this bond is the same energy as to break this bond. Hopefully that makes sense, okay? If making something releases more energy than it takes in, the implication is the atoms that make it up coming together is going to release energy to make it, okay? So that would be called a heat of formation. And a heat of formation, as the name suggests, is always to make that item, to make 1 mole of that item, how much energy is either going to take me or how much energy is going to be released. Okay, so to make the simplest example, if I had like water, right? To make water, let me grab my pen again. Right, to make water, you need H2 and you need O2. Remember, these are the standard states of these two elements, right? These are how they exist in nature, okay? By convention, we make these enthalpies, their heat of formation, for elements in their standard state, we make it 0. Okay, the idea here is that that's the normal condition in which it's existing in nature. And we're going to say, hey, for that to exist, it doesn't take any energy at all, doesn't release any energy, it's at baseline, and we make that 0. And that's true for every element in its standard state. Okay, so sodium is Na, standard state is Na by itself in the solid phase, heat of formation is 0. Okay, that's a convention, aka we just kind of agreed as chemists to make that 0 for each element. Doesn't matter which element, as long as it's in a standard state. Hydrogen and oxygen are diatomic. They have to be H2 and H2 and O2. They would still be 0. If it's H by itself, then it's different, okay? Because H to exist by itself actually takes energy. H doesn't want to exist by itself. It wants to exist H2. Same thing with O2, Cl2, F2, etc. The diatomics, okay? In any case, these are two diatomics in their standard state. However, these are going to make a compound called water, okay? And this will have what's called a heat of formation. How is it measured, you might ask? Like, how do we get this? How do we get a number for this? You as a chemist would measure out a mole of hydrogen, a mole of oxygen, and attempt to make a mole of water. I say attempt to because you may notice this reaction is not balanced. So if we balance this, a 2 there and a 2 there is now balanced. So what does this mean? If I took 2 moles of H2, put them in, like, imagine a jar, right? And then took 1 mole of oxygen, put that into the jar, I could then measure when they react, like a kind of like a thermometer sticking out of that jar, and basically measure how much energy is either released, temperature would go up, or would the temperature go down, in which case energy is being pulled. Basically, it sounds weird, right? If energy is going in, should the temperature go up? But the energy is going into the bonds. The energy is going into the substance, not the surroundings. The thermometer measures the surroundings, okay? Heats of formation are very rarely not negative. They're almost always negative because, again, making bonds releases energy. So for water, we need to know, hey, is this liquid water or gaseous water? If I make this, let's say, gaseous water, I believe the number is negative 285. I'm going to round it just there. It's a little bit different, okay? The unit, of course, is kilojoules per mole, okay? The implication is 1 mole of water will release 285 kilojoules when it's made. Now, this reaction says there's 2 moles made, so I could then multiply this by 2, and that would give me what? About 570, right? So we could say the delta H, the change in enthalpy. I should remember, I think, again, this video is, for the most part, you probably already watched me explain this to you, right? Enthalpy is H, which is kind of helpful. Think about heat, right? Delta change delta H in enthalpy of the reaction. In this case, it would be negative, again, this times 2, so that's going to be, what, 570, I believe, if my mental math is working. And this will just be kilojoules, because I multiplied it by 2 moles, which means the moles have canceled. Okay, it means this reaction as written will release 570 kilojoules. And again, how would you measure this? You would do this reaction, and you would measure how much energy it takes. Like you would have water in there, for example, and measure how much the temperature changes, and then we can use Q equals MC delta T, another calculation, to figure out how much energy it took. And guess what? It should, in theory, be 570 kilojoules. Okay. Now, this is for the reaction, right? Notice there's no moles. This would be per every 2 moles of water in this case, right? Or for every 1 mole of O2, or for every 2 moles of H2. Okay, sometimes you'll see it written a little bit differently, where instead of using whole numbers, they're going to try to just get this to be 1. And if you're like, well, you can't do that. Normally, yes, but in thermodynamics, sometimes we do this. We say, hey, give me, so we want this to be 1. We want, this could be anything, this could be anything, right? But if I want this to be 1, right, I still need 2 H2s. I'm sorry, bad. We need H2, correct? H2O. So H2 plus, now it's the O2 is the problem, so we'd put, believe it or not, 1/2 O2 yields H2O, okay? Now you might say, I don't really like that because I don't like using decimals, I don't like using fractions. Sure, the only difference would be what? Delta H in this case would be the negative 285 kilojoules, okay? And I'm going to tell you this right now, like this and this, yes, they're different numbers, but it's because of what? The balancing. Okay? I'm only showing you this to say if you look this up, if you were to Google this, go on YouTube, go on Google in general and look for this, you might see these fractions. And that's all it's doing, okay? That's more common, as a matter of fact, but in my opinion, especially if you're new to this, it's probably not worth the nuance, but that's an opinion. Okay, but hopefully it's making sense to you. All right, so we can calculate the change in enthalpy of a chemical reaction. Okay, now that's for a compound. That's for making water. That's how we get the heat of formation. But what about like something else? For example, what if I had, I think the example I wanted to give was, let's say we have hydrogen peroxide, okay, which is H2O2. Oops, that's not what I wanted at all. There we go. Let's try that again. H2O2 is hydrogen peroxide. So I have H2O2. This is in the liquid phase. And this matters big time because if you look up data, if you're like, hey, what's the heat of formation of hydrogen peroxide? You need to know, are we talking about the liquid phase or are we talking about the gaseous phase or potentially the solid phase, right? It's important you pick the correct phase because the numbers are very different. Okay? Hydrogen peroxide is going to decompose into oxygen gas and liquid water. Okay, so H2O in the liquid phase. Again, if it's steam, that would be the gaseous phase, right? And it matters. It's not like a little itty-bitty thing. That's why we're putting these letters to denote the phase of matter. Okay, is this balanced? Hopefully you're saying, no, it ain't balanced. We got too much oxygen, right? To get this to work, let's go ahead and double our water. That gives me 4 oxygens. I can get 4 over here by just putting a 2 in front. And would you look at that, my hydrogens are also balanced. So we are good to go. Okay, now I need my numbers. I need to look these up. Okay, I have them here. That's why I'm doing this one. I have them. Usually I don't write these down. Usually I just look it up for you. But you probably don't want to watch me fumble through a reference table. It's probably not very fun to watch. So let's see. The heat of formation of H2O2, hydrogen peroxide, the number I found is negative 190.75 kilojoules per mole. Okay. Oxygen's heat of formation is, hey, it's oxygen. It's in the gaseous phase. It's in standard state. Oh, that's going to be 0. Well, that's nice. And then water, I think we just found that earlier, is what, the negative 285, I believe, right? Notice I'm saying I believe. I'm pretty sure that's the right number. It's worth noting if you look up these numbers, there is some discrepancy you might see. You might find 284.7. You might find 285.8. You might find, but here's the thing. It's based on how it's measured. It should be close, okay? If you found gaseous water, then it's like 245 or something like that, 241, okay? That's because it's a different phase, okay? That's the idea here, okay? So now I can do, I can figure out the heat of formation. I'm sorry, the heat of the reaction, right? And to do that, we're going to use a fancy schmancy calculation, okay? Notice in the last one, we had the same answer as that for water, which was 285, right? And then we doubled it and we got 570. We can't just do that here, right? Because we have, yes, 0 here. That's nice. But we also have this number. So what do we do with it? We follow this equation. Delta H of the reaction, the change in enthalpy of the reaction, is equal to the sum of the heat of formation of the products times its molar coefficient. Okay, I'm writing this mathematically, so I'm not putting a number there. I'm putting n. N in this case is referring to the coefficient. Okay, we take this and we subtract the sum of the heat of formation of the reactants, I'm just abbreviating this rec to be easy to see, times its molar coefficient, n again. Okay, you might see it written slightly different other places, but it's the same thing. Okay, and then this just means we need to do what? Take our 190.75, that's a reactant, multiply it by n times 2. We take the sum. This sigma is sum. There's only one reactant. There's only one reactant. So, hey, that's it. Negative 190.75 times 2. Okay, that gives us a number. We're going to subtract that from the sum of the products. In this case, there's 2. Thankfully for us, oxygen is 0, so that one goes to 0. Easy. And then we have 2 moles of H2O times 285. So what does this look like? You say, okay, you've been talking, show it to me. Let's do our products first. 2 moles times H2O, which is negative 285. Okay, this is kilojoules. This is moles, right? Kilojoules per mole, right? The moles are going to cancel, okay? That is 1 we're subtracting. And then we have what? 2 moles of the H2O2, so then that's times negative 190.75. And then we need to use a calculator, right? So let's see what that looks like. So oops, that's not what I wanted. Using some parentheses are our friends, we say 2 times negative 1, oops. This is why I'm not a big fan of this calculator, by the way. You have to put it exactly right or else it gets mad at you. Parentheses, negative 285 times 2. So that's negative 570, what a surprise, minus, and then we have 2 times negative 190. So negative 190.75 times 2. Okay, enter, and we get negative 188.5. Okay, and that number is the change in enthalpy of the reaction. So if I react 2 moles of H2O2, I'm going to release, notice I'm saying release, delta H, negative 188, what was it, point, I don't know, something, 0.5, okay, 0.5. And that's just kilojoules, okay? Could you then take this and divide this by 2 and turn this into per mole of H2O2 produced? It's going to take, what, about negative 90 something? You could, okay? There's other ways you could work this. But for right now, that's our number, okay? This is exothermic. This reaction will release heat, okay? And again, theoretically, if I measure 2 moles of it, I should get that amount of energy out, okay? So that is enthalpy, and hopefully you followed me, hopefully it made sense, hopefully it's review for you, hopefully you're like, yep, it's easy for me, but just hopefully connecting dots here, okay? Big takeaways, this equation. Big takeaways, negative means exothermic, positive would mean endothermic, all right? Let's do entropy quick. Entropy is a harder concept to understand, but this video is mainly focused on the equation, okay? I'll see if I can make another video just over the concept of entropy. To do that calculation is very similar to the one we did. But real quick, entropy is essentially a measure of chaos, of disorder. Entropy is a consequence of the second law of thermodynamics, which says energy goes from high concentration to low concentration, which means energy spreads out. Entropy in chemistry, in the context of this, is saying, like, does a reaction make energy spread out more, or does a reaction basically consolidate energy, keep it close? Generally speaking, the universe hates that. When I say hates it, I mean like you're not going to see it happen commonly. The analogy I would give you is, if there's a sandcastle, somebody had to make the sandcastle. That doesn't happen by nature, does it? Waves don't hit sand and make a beautiful sandcastle with doors and windows. You'd be like, I don't think that happens, because that is ordered. The universe does what? A wave hits the sandcastle and destroys it, turns that beautiful Victorian mansion I built into a pile of sand, less ordered. Okay? So the implication here in chemistry is that there are reactions that make things more ordered. That's bad from the universe's perspective. And there are reactions that decrease order. And the universe likes that. Okay? Again, when I say the universe, I don't mean you and me. I don't mean like, hey, we like it. No, we usually try to put order in things. We're life. We're living things. Living things tend to make order. And the non-living things, or rather processes in nature, tend to do the opposite. Okay? Entropy as a measure is kind of weird. The unit is joules per Kelvin. It's like how much energy is available at a given temperature is how you can think about it. Even then, that's probably a little bit confusing to you, but that's okay, because guess what? Physics can be complicated, okay, believe it or not. But the point is this. We are going to do basically the same calculation in order to find what's called the change in entropy of a reaction. Okay, and there's a reason we're doing these two things. It's not just, hey, let's do calculations, right? The last thing, the Gibbs free energy, that's where we kind of tie these things together and have a nice, neat equation that is very helpful to us. But we'll get to that in a second. So what we need to do then is look up entropy values, okay? And these, again, are experimentally acquired. You don't have to memorize these. The downside of these, so if I write my reaction out, the downside of the entropy values is, unfortunately, they're never zero, okay? So with the heats of formation, sometimes you get lucky, right? You're like, oh, oxygen is zero because it's an element. Unfortunately, entropy is not going to be zero, okay? So you can't just say, oh, it's oxygen, it's going to be zero. Unfortunately, it's going to be a number that is non-zero, unfortunately, okay? So yeah, you have to look these numbers up. You can't just figure them out. Okay. Well, I guess you could figure them out if you do the math, but you get what I'm saying. All right, so balancing it, good idea. Yay. The numbers that I found for entropy for hydrogen peroxide, I found positive 109.5 joules per mole times degrees Kelvin. Okay, it's a mouthful. Notice it's joules. That's important. It's not kilojoules. And notice it's degrees Kelvin. That's also going to matter big time. The mole, of course, is because it's per mole, okay? Oxygen is, I think I found 205 joules per mole times degrees Kelvin. And then liquid water is, I think, 69.4 is the number I found. 69.4 joules per mole times degrees Kelvin. Okay, notice they're all positive, right? It is possible to have a negative entropy, but it's pretty rare, and there's a very good reason for that, okay? Basically, this is a measure of how much chaos there is. And even the most ordered systems, generally speaking, have some degree of chaos, okay? This idea of higher entropy values implies it's a better thing to transfer energy, to get rid of it, to spread it out, is how you can kind of think about this. That's how I think about it. Okay, so gases tend to have pretty high entropy values. Solids, liquids tend to have lower values. Okay, are there exceptions? Sure, but generally speaking, that's true. Think of it as this substance is good at spreading energy out, it's going to have high entropy. If it's poor at spreading energy out, then it's going to have a low entropy, okay, which hopefully is helping understand this, okay? So how do we calculate the change, right? Thinking about these words, right? The change in entropy. Entropy is S, yes, of this reaction. Luckily for us, it's almost exactly the same, except instead of enthalpy, heats of formation, we use the entropies. And it's the exact same equation. So what do? I take my products, multiply by their, products, multiply them by their moles, add them together, subtract then the reactants, multiply by the moles. It's easy, okay? The calculation shouldn't be that bad, hopefully. So what does it look like? Well, we got to write out the math fully. We have two products. We have 2 moles of H2O, so times 69.4 joules per mole Kelvin, okay, plus, remember, it's a sum, in this case, 1 mole of O2 times 205 joules per mole degrees Kelvin. These are my products, okay, and then I'm going to subtract my reactants. In this case, there's only one. So 2 moles times 109.5 joules per mole Kelvin. Okay, my little thing here is getting in the way, but you get the idea. Okay, and then of course we use our calculator. Okay, and hopefully I can get this thing to behave here. I'm not a huge fan of this calculator, but you can see it, I guess, which is nice. Okay, so let's see. We have 2 times negative. See that? I don't even know if that worked. 2 times. Yeah, it didn't work. Well, let's do this. Ready? Negative 69.4 times 2 plus. Let's do, what is it? Negative. See, and it's fine because when you add a negative, it makes it subtract, right? Minus 205 times 1 in this case, which is, yeah, which is the same number. Negative 343.8 minus. Oh wait, hang on. No. See, I caught myself because this calculator, I'm not a fan of it. Tell you what, let's do this because I do not like this calculator when it misbehaves like that. So let's do this. Not that it's misbehaving, but I hate having to enter it kind of backwards, if that makes any sense. If you're like me, maybe you're like, yeah, I agree. Maybe you're like, oh, you're just crazy. That's possible too, I guess. What did we have? We had 69.4 times 2 plus, and then what was it for the 205, right? 1 times 205, right? So that's what I have so far. Okay. Yeah, I think I put the negative in because I'm thinking of something else, right? So we then subtract, because that part does have to be negatives, subtract, whoopsie daisy, 2 times 109.5. 2 times 109.5, and we get 124.8. Positive 124.8. And the fact that it's positive, again, it matters big time whether you have a positive answer or a negative answer. Change implies are we getting more entropy or less entropy? In this case, more entropy, which hopefully you're saying that's probably a good thing, isn't it? Yeah, the universe loves that. The universe is a big fan of that. So 124.8 is our entropy of the reaction, the change in entropy. And what do we say? See, I keep forgetting it. 124.8? Uh-oh, wait, that's not the right one. 124.8? Oh. Yeah, 124.8, good. Okay, see? Long day. 124.8. The unit is joules per degrees Kelvin. Okay, that's going to matter big time in a minute, but, So that's delta S. Yay! Okay, if I asked you on a quiz, test, whatever, calculate the change in entropy, you would say that's the answer for this, for this reaction. Okay, for the decomposition of hydrogen peroxide, 2 moles decomposing, this is the change in entropy. Hopefully you're saying makes sense, got it. Okay, this leads then to the last bit, right? And I promise it won't be that long. I know this video is probably a little bit longer than I originally intended, but it's okay. At least I hope it is. And that is then. All right, well, what do I do with these numbers? Like, okay, sure, I guess I have a delta S, I have delta H, who cares? That's where Gibbs free energy comes into play. Gibbs free energy, to make it simple, again, for an intro to chemistry type class, is whether a reaction is spontaneous or whether a reaction is non-spontaneous. And the word spontaneous in this context means like, will it happen by itself? Like if I put these in a jar and I just go, and I watch it, will the reaction actually proceed as written left to right? If it's spontaneous, the answer is it will. Doesn't tell me how fast it'll happen, doesn't tell me if it's going to explode or happen over years, but it does tell me whether or not I can just observe it happening by itself without me doing anything to make it happen. Okay? That's what Gibbs free energy tells me. And you might say, well, what do you mean tells me? What does it tell you? Does it literally say it out loud? Well, if it's negative, it means it's spontaneous. And if it's positive, it means it's non-spontaneous, which means I would have to do something as a chemist to make the reaction happen. Okay? What's the equation, you might say? Because, hey, if it's negative, well, how do I know if it's negative? Well, you know it's negative, or you'll know it's negative, I should say, if this equation is true. Delta G, the change in Gibbs free energy, is equal to the enthalpy change minus the change in entropy times the temperature in which you are trying to do the experiment, trying through the reaction. Okay? This equation looks pretty easy because it is. It's a pretty easy equation to work with, but you got to be careful. Number one, you got to make sure you find delta H and delta S correctly. If you don't, you're not going to get an answer. Secondly, the units matter big time. Delta H is in kilojoules, right? Delta S is in joules per Kelvin. You cannot subtract kilojoules. You cannot subtract joules over Kelvin from that, can you? And if you're clever, you're probably saying right now, oh, well, that's why T is here for temperature. And if you plug in a temperature in degrees Kelvin, that will get rid of the degrees Kelvin. And that's right. Exactly, right? Math works. It's almost like there's a reason we teach it to you, right? That's nice. Degrees Kelvin go bye-bye. Hopefully, you're saying, yeah, but what about the joules? And I would say exactly. You have to convert the joules to kilojoules. Or you could, if you want, convert the kilojoules into joules and then just keep them together, aka convert delta H to joules. I wouldn't recommend that, though. I would recommend converting delta S into kilojoules, okay? And if you're going, well, how am I supposed to do that? It's very easy, right? Joules to kilojoules. You just divide by 1,000, because 1,000 joules is a kilojoule. Just like 1,000 meters is a kilometer, 1,000 grams is a kilogram, right? It's the same thing. It's almost like that metric system's got something cooking for it, okay, going for it. So if I were to look at this, we had a delta H, right, of our reaction. That was what, negative, what did we have? Like negative 188 or something like that, right? And then we had a delta S of the 124.8, okay? If you were to plug those numbers in, I think it was negative 188, right? Kilojoules minus our delta S now. Yes, it's 124.8, but I'm going to divide that by 1,000. I get 0.1248. Now it's kilojoules per Kelvin. And then you might say, what about the temperature? Like, do I just plug in a T value? Do I just pick one? We usually are going to default to this specific temperature, 298 Kelvin, which incidentally is called standard temperature. Okay, standard temperature is, again, like by convention, kind of like the baseline of what we use. You might say, how come not 0? Well, 0 degrees Kelvin is absolute 0. We're not going to use that, because nothing can happen at absolute 0, right? So we pick room temperature. Room temperature in Kelvin is about 298. Truthfully, it should be a little bit lower in my opinion, because room temperature is not 77 degrees for most people, right? Room temperature is probably like 72. But 298 is what they picked, okay? 25 degrees Celsius is what it is, okay? Not the end of the world. I hope you're not going, I hate this now. I mean, I don't know. It's slightly warm, I guess, right? But 298 Kelvin, okay? And again, what happens here? The Kelvin cancels because this number, remember, now it's kilojoules per Kelvin, okay? And then what we're looking for is delta G. And all I got to do is multiply this by this, subtract this, and if my answer is negative, it means spontaneous. If my answer is positive, it means it's non-spontaneous. So again, if I plug those numbers in, let's see what we get. Let's see, do I have the history for this? Does it have the history? Because then I could actually figure out. Oh, it is. It's right here, isn't it? Yeah, negative 188.5. Good. Okay, good. Remember how I was like, oh, is it negative 188? So let's plug those numbers in. So negative 188.5 minus, I'll just put this in parentheses just so we're clear, 0.1248 times 298, and we get negative 225.6904. That is the delta G. That is the Gibbs free energy. What did I say? I say these numbers and I forget them instantly, which, is kind of silly. Negative 225.69, we'll say. So negative 225.69. The unit would be kilojoules, right? But what we really care about right now, what really matters for us is this. It's negative, which means at 298 degrees Kelvin, this reaction will proceed. This reaction will occur spontaneously, okay? Hydrogen peroxide will, at room temperature, decompose. That's not just theoretical, that is observed. Like, I can tell you that for sure, that is true, okay? That will happen. However, it does not tell me how quickly. You might be tempted to say, well, the number's big, 225 is big, it must be fast. It doesn't really mean that, unfortunately, okay? You would need to figure out what are called the kinetics of the equation. Thermodynamics just tell you, will it happen? Like, is it favorable? Does the universe want it to happen? That's all it tells you. Kinetics is how fast, right? Like, if I'm watching it and I'm observing how quickly, how many moles per second, right? If it's making gas, how many liters per second is it making, right? And as you can imagine, that can be important. I mean, like, you might have a reaction that's super slow, you want to speed it up. There's ways to do that, right? But thermodynamics just tells you, will it happen? And in this case, it will. You could then ask yourself the question, at what temperature is it not spontaneous, right? Is there a temperature in which it's not spontaneous? And to do that, you may want to think about setting delta G equal to 0. The idea here being if you're at 0, if you go slightly below it, right, it's spontaneous, slightly above it, non-spontaneous. The idea is you can find a temperature where you're right at that, like, break-even point. And the implication is if you go above that temperature, depending on what it is, or below that temperature, that would be the spontaneity point, right? Like, that's the idea here, okay? But you would just solve for T. Instead of picking 298, you would just algebraically solve for T, and then based on that, you'd have the temperature in which the reaction is spontaneous. You might find that there is no temperature at which a reaction is spontaneous. You could have scenarios, and I'll probably make another video going over this, where there could be there's no temperature in which it's spontaneous. And the idea then is that the universe really, 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 really hates that reaction, that it'll never happen in nature, okay? Or rather, it will require things to happen that are really putting energy into that sucker and making it work, okay? Ready for this? Humans can do that. We can channel energy into things and do all sorts of crazy things, right? Other sources of life can do that, okay? But nature, generally speaking, no. Right? There's exceptions, of course, but they're like unlikely is the idea. Okay, so hopefully this video makes sense. Hopefully to you. The name of the game with this is you practice it a couple times. I don't think the calculations are really that bad. It's really just knowing what they mean and then understanding how to use them is maybe the hard part. Okay, so have a great rest of your day. I hope this video helped you, and see you next video.